everyone, and welcome back to my channel. My name is Dave. If you're a subscriber, I know I've been away for a while, but I hope to be making more videos in the near future, so please stay tuned for updates. Anyways, today I'll be taking a look at the mathematics admissions test, which is used to grant admissions to Oxford University in the UK. The MAT aims to test a depth of mathematical understanding rather than a breadth of knowledge like the American SAT, which also tests for proficiency in English. It is also somewhat harder because it covers the basics of differential and integral calculus, whereas the SAT does not cover these topics. So if you've had experience with this test in particular, or just in general with the British math curriculum, please feel free to comment down below what it was like preparing, studying, or just taking this test. That said, let's get started. As I'd like to keep this under 10 minutes, and that won't be enough to talk through all of the questions, please subscribe to my channel if you'd like to see more questions from this test explained. In this question, they ask us to find the area of a dodecagon inscribed inside a circle with a radius of 1. Now, a regular dodecagon is comprised of 12 isosceles triangles, each having an angle of 30 degrees and side lengths of 1. The area of a triangle can be given by 1/2 AB sine theta, and hence one triangle has the area 1/2 times 1 times 1 times sine of 30, which is also equal to 1/4. And 12 triangles would therefore have an area of 3. And that is the answer for this question. In this question, they want us to find the value of a in this equation that contains a as one of the limits of integration. In order to do this, I will first evaluate the integral, which gives us 2/3 times x to the 3/2 power plus x cubed over 3 evaluated at a and 0. Plugging in the limits of integration, I get 2/3 times a to the 3/2 power plus a cubed over 3. Now what I have to do is set this equal to 5, and when I do this and I rearrange it a little bit to make my life easier, I get 0 is equal to a cubed plus 2 times a to the 3/2 power minus 15. Now I'm going to let a to the 3/2 power equal t, and I get 0 equals t squared plus 2t minus 15. This can very easily be factored as 0 equals the quantity t plus 5 times the quantity t minus 3. I can solve this and I would get t equals -5 and t equals 3. However, the question only asks for the positive values, so I'm going to eliminate t equals -5. Now I use the fact that I substituted t equals a to the 3/2 power to back solve and find that a is equal to 3 to the 2/3 power. In this question, the first step is to find the intersection of two curves. So we set e to the x power equal to 1 minus e to the x power. This gives us 2 times e to the x power is equal to 1, or e to the x power is equal to 1/2. Since we don't have a calculator available to us on this test, we just write down that x is equal to the natural log of 1/2. The next thing to do is to set up the integral. Since the natural log of 1/2 is clearly negative, this goes on the bottom, and 0 will go on the top. Inside the integral, we have e to the x power minus 1 minus e to the x power with respect to x. We can condense this a little bit and get the integral from the natural log of 1/2 to 0 of 2 times e to the x power minus 1 with respect to x. The next step is to evaluate the integral, and we have 2 times e to the x power minus x evaluated at x equals 0 and x at the natural log of 1/2. Evaluating this further gives us 1 plus the natural log of 1/2. However, since this isn't one of the choices, we rewrite the natural log of 1/2 as 1 minus the natural log of 2. And this problem is now complete. In this question, we have 6 vectors, v1 through v6, and they can be either 1, 1 or 3, 2. What we have to do is calculate the probability that the sum of these 6 vectors is equal to the vector 10, 8. To do this, we have alpha times the vector 1, 1 plus beta times the vector 3, 2 is equal to 10, 8. This gives us a system of equations. Alpha plus 3 beta is equal to 10, and alpha plus 2 beta is equal to 8. Solving this system of equations gives us alpha is equal to 4 and beta is equal to 2. This means that 2 of the vectors have to be equal to 3, 2, and the remaining 4 are simply 1, 1. So in other words, we have to choose any 2 of these 6 vectors, v1 through v6, to be equal to 3, 2, and let the rest be equal to 1, 1. This can be done in a total of 15 ways because there are 6 ways to choose where to place the first 3, 2 vector and 5 ways to place the next 3, 2 vector. However, since the order doesn't matter, we divide by 2. And there are also 2 to the 6th combinations total. This gives us a probability of 15 over 64, and that's the final answer for this question. In this question, question F, we are asked to find the number of values of a for which the tangent line also passes through 2, 0. To find the tangent line, we begin by finding the first derivative of y equals x cubed minus 3x, which of course is 3x squared minus 3. We then put this into our point slope form to get y minus the quantity a cubed minus a is equal to the quantity 3 times a squared minus 3 times the quantity x minus a. We then insert the value of x equals 2 and y equals 0 so that we get negative quantity a cubed minus a is equal to 3a squared minus 3 times the quantity 2 minus a. This will be true if the equation is true, so we rearrange the equation to get 0 is equal to 3a squared minus 3 times the quantity 2 minus a plus the quantity a cubed minus 3a. Simplifying this and reducing it into its standard form, we get 0 is equal to a cubed minus 3a squared plus 3. Now the tangent line contains 2, 0 for the values of a that satisfy this equation as we said before. So we have to solve this equation, or we can also produce a rough sketch of the graph by using the first derivative of this expression in a. So this first derivative is 3a squared minus 6a, but it can also be written as 3a times the quantity a minus 2. Which tells us that there was a local maximum at a equals 0 and a local minimum at a equals 2. Evaluating this expression, a cubed minus 3a squared plus 3 for a equals 0 and a equals 2 gives us 3 and negative 1 respectively, which means that since this is a cubic, the graph will start at negative infinity, then it increases to y equals 3 when a equals 0, then it will decrease to y equals negative 1, and then it will increase without bound to y equals positive infinity. Because of this, this means that there are exactly 3 zeros. So D is the correct answer. Okay, so in this question, we want to find the sum of sine squared of 1 degree plus sine squared of 2 degrees plus sine squared of 3 degrees and so on, all the way up to the sine squared of 89 degrees plus the sine squared of 90 degrees. In order to solve this, we will be using 2 identities. The first is sine squared of theta plus cosine squared of theta is equal to 1. The second one is sine of 90 degrees minus theta is equal to cosine of theta. With these 2 identities, we can rewrite the question in the form sine squared of 1 degree plus cosine squared of 1 degree plus sine squared of 2 degrees plus cosine squared of 2 degrees and so on, all the way up to sine squared of 44 degrees plus cosine squared of 44 degrees. This gives us 44 pairs, but we still have to account for sine squared of 45 degrees plus sine squared of 90 degrees. The 44 pairs gives us 44, and sine squared of 45 degrees is 1/2, and sine squared of 90 degrees is 1, thus giving us a total of 45.5 as our final answer. Right, I think this is a good place to stop. However, if you're interested in seeing the rest of these questions and more questions like it from the MAT and other tests, please feel free to hit like and hit the subscribe button. Once again, my name is Dave, and I want to thank you for watching my video, and I'll see you next time.